Hi all, welcome to the first reinforcement learning lecture. I'll be the one doing the reinforcement learning lectures for this course. I'll be starting off simple with the basics and then move slowly into more advanced deep reinforcement lectures where we'll be using a neural network methodology within reinforcement learning. In reinforcement learning, what we try to do is we try to train an agent to act in an environment. And the goal of this agent is to maximize reward. This is going to be explained a lot more in detail in the coming slides to see really how this works in practice. So let's first compare it with what we know already about the two learning paradigms you've seen before, namely supervised learning and unsupervised learning. So in supervised learning, we know exactly what to do. We get clear feedback on exactly the action to take. So you could say it's basically like imitation learning. We try to imitate a robot, for example, not a robot. We try to really do exactly as this other robot does. In reinforcing instead, we try to optimize some kind of signal. We try to optimize some reward, but we don't really know what actions to take. We have to try it out ourselves and see really what works well and really what kind of rewards we get from that to maximize that. So there is much less feedback given. We only get a reward in some kind of distant future, and we don't get a feedback in terms of what exact action to take. It's also different from unsupervised learning, where we have to kind of try to find some structure in our data, but there is no clear reward in supervised learning. We do have some rewards, some kind of clear signal to optimize, namely the reward we get from the environment. We'll mainly be talking about deep reinforcement learning, which is basically saying, okay, we're going to use neural networks for everything. So we're going to use neural networks to decide what actions to take. The thing that decides what actions to take is usually called a policy. This all happens within a reinforcement learning loop. This basic reinforcing loop is very simple. We start off with some state, st. This state is given to the policy. So this neural network that decides what actions to take. It takes its action, at, and its action is usually in an environment to come up with a new state and a new reward. And this keeps on looping and happening again and again and again. This reward is used to update our learner. So our learner is going to use the reward and all the actions it takes to find out how to improve the neural network to perform better in the future. That's in the end the goal. So a very simple example of one of these problems is a cart pull problems. We have this cart on which there is a pole, and the cart has to balance the pole to make sure it remains upright. It gets a positive reward of 1 if the pole remains upright, and otherwise it's 0. So that's how you would model the reward in this case. As a state, the state is basically the angle of the pole. So does it look like it's almost going to fall, or is it actually upright? It's also a very simple state, it's just a single number actually. The state is used by our policy. It's going to decide what to do next. Usually, in this case, we only can actually do two things, namely we can move left or right. That's what the car is going to do. So you're going to decide are we going to move left or right. This is going into the physics engine, and that together is going to create the next state, namely the next angle of the pole, and whether we succeeded at remaining upright. In this lecture, we'll be looking at the simplest deep reinforcement settings. So we'll only be discussing episodic, online, and for a while model-free methods. So don't worry really about what that means. We'll get into it a bit, but it's not that important. And we'll only be looking at neural network policies. So our policies are always going to be neural networks. We're not going to look at linear models or support vector machines or decision trees or whatever. That's also a possibility, but that's for another time. We're going to focus on gradient estimation, and I'll be discussing later on what that means. So for a very nice example is this DeepMind paper, a very old DeepQN paper. So basically the goal here is to learn how to destroy the blocks up there, the colored blocks. So it does this by moving this bed around. So the actions basically that can be taken are move left or move right. And the goal is to have the ball, in like a pong way, move it in or out and break all the blocks and make sure that the ball doesn't fall into the gap, which is a terminal state. So in this case, what is a state? Well, the state is just an image, namely what you would see as a person if you were to play this game. It's exactly just that, the image. So we can use CNNs for that, for example. And the reward is basically we get high reward if we break many blocks. And we keep training this. So after 240 minutes of training, we are right here in this case. So we do very well here. We get a very, very well-performing agent that really is able to always keep up the ball. And now it does something very fancy, namely is able to get the ball above the blocks and immediately remove a lot of blocks and get a lot of points. So that's great. It is able to learn this problem, even though it's very hard, using just the image. So how would a neural network look like? So this basically just depends on the kind of data you have. So in this case, we have a state that is an image. So, we've seen this before in the CNN lectures. We use a convolutional neural network, take a few convolutional layers, and use a fully connected layer, and then we get a multi-class categorical output distribution. So this is just as you would do in image prediction for memories. You basically have some amount of options that we can choose from, namely move left or move right. And we choose one of these using some kind of classification, right? Of course, we train it differently because we don't know what action to take. But this kind of networks look just like you would if you were doing supervised learning, essentially. The networks actually kind of like look just the same. We won't be discussing any further details about neural network architectures. It's basically just try to choose a neural network architecture that best suits the data, like you would usually do when you use deep learning. Next, we talk about the three main components of reinforcement. That's actions A, states S, and rewards R. These are all random variables, so they are all distributed using some kind of distribution. We'll be going into what exactly that means. Together, we get a trajectory. So we start off in its initial state as 0. From there we take an action, get a reward from that action. Then we are again in a new state, again from a new action, get a reward, and it keeps on repeating until we get to some kind of terminal state as capital T. From here we're going to stop running and we get the end of the trajectory. So these trajectories we'll be talking about, these are indicated by tau, this T symbol. So let's just look at a bit of a trajectory. So again, we're going to look at this breakout problem from Atari. So we're in some state, which is an image. This image is passed into our policy network, a CNN. Then we predict an action, namely go left. And then from taking this action, we actually got no reward. Nothing really happened. Just the ball moved a bit further and the bat moved to the left, as you would predict, because we did that action, right? So let's do this again. Put it into our pulse network, predict a new action, namely again move left. And we actually got a reward because our ball broke one of the blocks up there. So we get a +1 reward. Great. So what exactly happened here? Okay, we got a positive reward. But why did we get a positive reward? So what action caused this reward? That's actually way back when we got the bat to bounce back and move into the air and break some block. But these two actions that we took just now, moving left, that didn't really cause any reward, right? Because, it just moved left, but the ball was already in the air, so nothing really happened that caused this reward. So this is the credit assignment problem. So what action causes what rewards? It's a very hard problem, and we'll be looking into it a bit more. We model reinforcement learning problems using Markov Decision Processes. That's a scary name, and it is not scary, But don't worry, we'll be going through it and we will see simple examples of how this works. So we talked about this action, states, and rewards, and this trajectory is tau, which is a sequence of state, action, reward. It keeps on repeating. And then a Markov decision process basically models the probability of a trajectory given the parameters of the neural network theta. So this is what it looks like. It's a scary, kind of scary maybe, distribution, but it's actually pretty simple when you look at it from a, generative perspective. And we'll be doing it for several times to really get into what exactly this means. So it basically says that the probability of a trajectory is made up of different probability distributions over these symbols within the trajectory, so over the different states, actions, and rewards. So we start off by the initial state as 0, and we're going to look what is the probability of this initial state. That's the first probability on the left, so P of S0. Then this product is basically a loop over all the states after that. So we go from the zeroed state up into the terminal state. So for every time step we're going to see what's the probability of taking an action using this pi theta, and we're going to see the state transition distribution P of st rt plus 1 given st at. So this is basically saying, is basically the environment. It's basically saying if we have a state and we have an action and we perform the action in the state, what's then the distribution over the next states and the rewards we get in that state. So to visualize this a bit more, and we're going to use computation graphs like we did before. I'm going to introduce a bit of new notation, namely this diamond shape with a tilde into it. So that's the wave thing. This basically means sample from a probability distribution. So basically means take a sample from, in this example, the initial state distribution, and concretely choose one exact initial state. We're also going to use these dotted lines, dotted arrows, and this basically means that these are non-differentiable paths. So we're going to use it more in the future. So here we take initial state, we sample it from distribution, and we see what happens. So next, we're going to take an action in that state. So we use a state that we just sampled, and we're going to use the parameters theta to choose what action to next take. This action is A0. The action we take in the initial state. And we sample that, importantly, from the policy distribution. So the policy network, which is a neural network, that takes in the state as 0 and gives a categorical distribution of all options. And from this categorical distribution, we're going to sample one A0. That's great. So we use this initial state and the first action we take, and we use that in the state transition to sample a new state in a new reward. So we completely sample from that, and we get a reward and a state in the next time step. So the second time step we start with 0. But yeah. Note very well again that there are many dotted lines, or many paths that are not differentiable. This is because sampling is not differentiable. It's actually a non-differentiable operation. That's one reason. Another one is that the environment is not differentiable. We'll get into this more because it's very important for thinking about what kind of algorithms we can make in reinforcement learning. This loop basically keeps repeating. So we're in a state S1 now. We're going to use that in our neural network, our policy distribution, and we're going to choose an action from that A1, and together it's going into the state distribution, state transition distribution, to transition into the next state, into the next reward, which we are again going to sample, blah blah, keeps repeating, etc. etc. Importantly, we always use the same set of parameters here. There's all the same parameters theta that is used to decide what action to take. So this is why the MDP is dependent on the action, the parameters theta. Markov decision processes make two key assumptions about what kind of problems and environments we work in within reinforcement learning. The first is full observability of states. This basically means that we know everything about the states that we are currently in. This is actually usually a wrong assumption. So think about poker, where you don't know the hands of other people that you're playing against. So you don't have complete observability, you have partial observability. This can be modeled in extensions like MDPs, partial observable MDPs, but that's out of scope, so I will not be talking about that. The second key assumption of MDPs is the Markov assumption. The Markov assumption basically says that the current state is independent of the history of the state that came before, given the state that came right before the current state, as t-1. So in probability distribution terms, it basically says that the probability distribution of the current state given the previous action and the complete history, so from time step 1 or 0 until the previous time step, is exactly the same as the probability of the current time step, the state in the current time step given the action we took in the previous time step, and not the rest of the history. This property is actually used to derive very strong algorithms because it allows us to do many simplifications that we would otherwise not be able to do. So a lot of reinforcement learning theory and algorithms are dependent on this property. Next, I would like to talk about rewards. So what exactly do they look like, and what can you say about rewards within reinforcement learning? Again, remember that the goal is to maximize this reward. We can talk about reward as the total reward we get throughout all the states that we visit. So that's just a sum of all the rewards. But usually we talk about the discounted reward. That's basically saying that we multiply all the states into the future, all the rewards in the future, by a gamma, which is a discount factor. This discount factor increases, so it's basically exponential in the future. So rewards in the very far future, they count way less to the total reward we get than rewards that are soon. So the total discount reward basically says we prefer rewards sooner rather than later. And this happens by this exponential decay through this discount factor gamma. The goal in reinforcement learning is then to maximize the total discounted rewards. But remember that rewards and states are stochastic or random variables. So if you follow the trajectory, you might get one sequence of rewards. But using the exact same parameters of your pulse network, you might also, because things are stochastic, do something very different. Because you might use a different action, or the environment is stochastic and you move into a state that you didn't expect to get into. So because everything is stochastic and we deal with random processes, we have to maximize expected return instead. The expected return is denoted by J. J is basically saying what is the expected return given that we execute an MDP with parameters theta. So sample a trajectory and see what we want to get. We'll get into that later. Now that we defined this J, we can basically say we want to optimize the parameters and get the maximum amount of expected reward. All right, so we want to maximize expected return. What does that mean exactly? So J is the expected return. So sample the trajectory, then look at the total discounted reward. What exactly is an expectation over trajectories? It's basically saying, okay, a trajectory might go this way or this way or this way, and we all have to look at every one of them and see how much reward we get, and we have to weight them by the probability of sampling that distribution, that trajectory. So clearly that is not doable because there are way too many trajectories that can be thought of. So instead what we do is Monte Carlo sampling. Monte Carlo seems fancy, but basically what it says is we take a sample and see what happens. It's not that complex. So let's look at a Monte Carlo estimate of the expected return. So let's look at a Monte Carlo algorithm, which is, again, just a sampling algorithm. So we take an initial state. We sample initial state from a distribution, which is S0. Then we're going to set the time step to 0. And as long as we have not visited a terminal state, we're going to keep looping. What we do first is we're going to sample a action from our policy network, which uses the current state to determine a distribution of possible actions. From the distribution, we're going to sample a concrete action to take. This action is then used together with the state to determine the next state and reward. Note this algorithm just follows exactly the stochastic computation graph we described earlier on, that you can see on the right. It follows exactly the same sequence of steps. We keep looping and looping and looping until we find a terminal state. So we sample an action from our policy distribution. Then we sample a state and reward from the transition distribution. We keep doing that. We keep track of all the rewards and then return the total discounted reward. Again, using this discounting factor. This is a Monte Carlo estimate of the expected return. So we get an estimate of how the kind of reward we would get if we were to follow this policy over our Markov decision process. Of course, we want to learn, so we want to maximize this. So we want to find the parameters theta star that maximize this expected return. This is of course very hard because many things are not differentiable and we have to take samples. So how do we do this? One way is policy gradient methods. So these methods, they estimate the gradient of this J function, this expected return. And using this gradient, we use gradient ascent to find new parameters. So just a very simple learning rule where we use the learning rate and multiply that by the gradient to find new parameters, right? We have needed to be very, very, very careful that this is a gradient ascent step and not a descent, because we want to maximize reward and not minimize it. So a small recap for this part. In reinforcement learning, we have agents that act in an environment to receive rewards. And reinforcement learning is modeled using Markov Decision Processes, which assume that we have full observability of states and that our history is independent of the future given the last state, otherwise known as the Markov assumption, which is very key to developing reinforcement learning algorithms. Next, we're going to look at policy gradient methods. These are methods that estimate the gradient over the expected return. And then we're going to use these into gradient ascent.